Okay, fluids. What's that?
An iceberg.
An iceberg.
Liquid or gas?
Oh, you're answering the question first. Okay. You're getting ahead. This is an iceberg. About what percentage of the iceberg is below the surface?
75.
I think it's
90.
88 actually, but yeah, like you're 89%. But we will figure out how to calculate that later in this chapter. So you will be able to figure out, based on what thing is floating in what, how much of it will stick out. Okay? All right. I know it's very exciting. Okay, so some very, very basic definitions. Fluids take on the shape of and exert pressure on their container. Okay, so if we have a container, it's a two-dimensional container, sort of a cartoon version, but here's a solid. What is it's incompressible. What do we mean by incompressible? You can't smush it, right? So you can't change its structure very easily. Liquids also incompressible. So it doesn't mean like you can deform it, right? It's about the volume. So can you press on it and change the volume? Okay. And you know, obviously there's like bulk strain and all that stuff because engineering. But generally, in an ideal situation, we don't compress. Okay. Gases are compressible, and what are some uses for compressing gases?
Storing water.
Storage, yeah. Like if you want to go scuba diving, right? You don't want to take a tank of uncompressed air because then you'll just float and it will be a pain. Yeah. So basically, that's the only application I can think of. Scuba diving, very important. Yes.
Changing temperatures. So if you want to compress something to have a cold area, then you expand it somewhere else.
Oh yeah, that's a good idea. We do that.
You
Yeah.
could also use it as like energy storage. So like some vehicles have gas charged shocks, so you can use it as a spring.
These are all really good examples. Good job, guys. All right, so yes, gas is compressible, so you can change the volume by applying forces, and you can use it to store energy. Which of these states of matter count as a fluid?
Last two.
Yes, liquid and gas. So solids, not fluids. But from a physics perspective, fluids are both liquids and gases. Okay, they behave using the same set of equations for the most part. All right, with some variation. So solids, not a fluid, which seems somewhat obvious, but gas is a fluid, slightly less obvious. So when you're talking about airplanes flying through the air, that is a fluids problem. Okay? Even if they don't end up in the ocean. Okay. So volume. Volume is just length times width times height, right? Okay. So units, meters cubed. Or, fun fact. If you have 1 meter cubed, how many cubic centimeters is that? 10 to the what?
Third?
10 to the
Ninth. Yeah, ninth.
No?
6.
6. Okay, why? Okay, so if you have 1 meter cubed, that's 1 meter cubed. Now remember, 1 meter is equal to 100 centimeters, but like we said, in order to get 1 meter cubed, we have to cube both sides of this equation. All right, so that means 1 meter cubed is equal to 100 cubed centimeters cubed. So 1 meter cubed is equal to 1,000,000 centimeters cubed, or 10 to the 6th centimeters cubed. It's important to remember the cube. So how many centimeters are in?
10 to the 7th.
Yeah, 100 centimeters in a meter, and then you have to cube that. So that will give you 10 to the 6th. I'm telling you this, I mean, you're like, oh, that's really obvious. People fuck this up every year. So now you know, okay? If you're going from a centimeter cubed to meters cubed, what do you multiply by? 10 to the negative 6. Okay, so it's never going to just be 1 to 100 when we're talking about cubed. For area, you have the same problem. It should be 10 to the 4th or 10 to the negative 4th. So be careful on those conversions, because I think people are like, oh, centimeter, there's 100 of those in a meter. Don't forget to square or cube it, okay? All right, we're starting off real easy today. which one is heavier, a kilogram of feathers or a kilogram of rocks? Assuming we're all on Earth.
Same as 1 kilogram.
And they have the same mass. What is their mass?
1 kilogram.
1 kilogram. But sometimes people say that the rocks are heavier. What are they talking about?
Density.
Density, okay? So density is very important, and density is usually a property of a particular thing. So for instance, if you take this piece of chalk, right, and you break it in half, I'm not going to because it's nice chalk, okay? But if you break it in half, and let's say one piece is really small and one piece is really big, so not really half, like 1/4 and 3/4. Which piece is more dense? It's all the same density, okay? So density ends up being a material property most of the time, and we can get volume and mass from the density. So, yeah. All right. Oh, yeah. And mass density, and we have to call it mass density because mass over volume. What other kinds of density have we dealt with in physics? Charge density, right? So charge density would be charge over volume, or charge over area, or charge over length. So this is actually volume mass density, which is mass over volume. Straightforward, okay? If you want to write it symbolically, rho is the symbol for volume mass density, or any kind of volume density, really, because we use it for charge too. And that's mass over volume, okay? And of course, if you're calculating density, mass is in kilograms, volume is in meters cubed, so kilograms per meter cubed. Although often it's given to us in grams per centimeter cubed, hence fun with conversions, okay? So make sure you know how to convert back and forth. Now, this is not totally straightforward because grams, not kilograms, centimeters, not meters. So this one doesn't go by 10 to the 6th, right? There's 1,000 factor and a 10 to the 6th factor. Ends up being a little bit more like 1,000, okay? All right, so mass density, mass over volume, looks like that. Density of water is the easiest one to remember. It's 1 gram per centimeter cubed, okay? So if you don't have to memorize a lot of stuff in this class, but that one is pretty easy to remember, and it comes up a lot. And is this true for other liquids, other fluids? No, just water. Okay, water is special. And I'm pretty sure we designed density to work like this. Like, I only messed up the other units to do this. So, or it just is a great coincidence. I'm not 100% sure about either. I had to change my 190 slides because they changed how we measure kilograms now. So, yeah. Anyway, I know you guys are all really
I have a video on units.
excited. You have a video on units? Okay, so you're excited.
Yeah.
Okay, so 1 gram per centimeter cubed, 1,000 meters, kilograms per meter cubed. Okay, and so whenever you're going back and forth between these two units, there's a factor of 1,000, so 10 to the 3. All right. Okay. Let's try a problem. Okay. All right. So this is a relatively simple problem, and we're not going to go through our whole process of drawing out everything, although I guess we could draw a cube. So here's a cube, right? And it has a length of 10 centimeters on each side. So that's this dimension and this dimension and this dimension, okay? So the first thing we're going to want to figure out is the volume. Now the volume of the cube is just going to be base times height times length, which we know are all 0.1 meters, because remember 10 centimeters is 0.1 meter. And then we're going to cube that. So that's going to give us 0.001 meters cubed, okay? Then we want to remember that density is mass over volume. So that's us writing our equation. And we can rearrange it so that we can solve for mass, and that's volume times density, or density times volume. So if we want to figure out the mass of the cube, then we just have to multiply this volume times whatever density we have for the particular material. So if we want to talk about styrofoam, okay, then we want to multiply to get the mass of styrofoam the density of styrofoam, which is going to be 30 kilograms per meter cubed, times 0.001 meter cubed. This is going to give us, sorry, that got a little messy, 0.03 kilograms, and you'll notice that we get some cancellation here. So this meter cubed cancels with this meter cubed, giving us kilograms. All right, and then we can just repeat this process for these other densities. So if we want the mass of water, we need the density of water times this same volume. So that's going to be 1,000 kilograms per meter cubed times 0.001. We're just moving decimal places around. So that's going to give us 1.0 kilograms. And once again, you'll see that this, oh, we should have put meters cubed here, but these will cancel. Okay, same thing with lead. So if we want the mass of lead, that's going to be the density of lead times the volume of our cube. So that's going to be 11,340 kilograms per meter cubed times 0.001 meter cubed, which is the volume of our cube. And that's going to give us 11.34 kilograms. So we started with something that wasn't very dense, and that cube didn't weigh a lot, right? Didn't have much mass. Then we moved to something a little more dense. We got more mass. Now we have a little bit more mass. Lead's pretty dense, but now we have something really freaking dense. So if we want the mass of a black hole, that's going to be equal to the density of a black hole times the same exact volume. So that's going to be 2 times 10 to the 30th kilograms per meter cubed times 0.001 meter cubed. That doesn't do a whole lot of damage. And we still get 2 times 10 to the 27th meters cubed, which is, let's just say, as you go down, things get very massive. All right? And that's what we would expect as we increase the density.